Hello students, in this video we will discuss about the Ampere circuital law. Ampere circuital law is given for the determination of the magnetic field intensity at a point. Actually it is the analogous to the Gauss theorem, Gauss law. Okay, so it plays the same role in electromagnetism as the Gauss law plays in the electrostatics. See what is its statement. It states that the magnetic field, the line integral of the magnetic field around the closed path is equal to the mu naught times the net current I threading through the area enclosed by the path. That is the line integral of the dot product of magnetic field intensity and the small length dl. Okay, it is always equal to the mu naught times of the current passing through the loop. Okay, see the example. Suppose this is a straight wire. This is a straight wire. So to find the magnetic field due to this current carrying straight wire, we have at the distance r from the wire at the point P. So to apply the circuital law, it is the condition to apply the circuital law. We have draw a Ampere's circle, just like we use in the Gauss theorem. Okay, Gaussian surface. It is similar to the Gaussian surface to apply the Gauss theorem. And here we have to draw this line. Okay, this is the Ampere circle. So take that distance as the radius, and we can draw from the P point, from this, taking this point, that is the through which the wire is passing, as a center. Okay, so at the distance P, which is at the distance r, which is the radius of this circle, we can find the magnetic field intensity. So this is the statement, dot product. So see, how can we prove it? You know very well, according to Biot-Savart's law. According to Biot-Savart's law, the magnetic field due to the current carrying straight wire, it is given by B is equal to mu naught upon 2 pi I upon R. We have derived already this formula. Okay, now we have to prove the Ampere circuital law using this Biot-Savart's law. So see, the line integral of the B and dl, this circle, it indicates that it is for the closed surface. It is for the closed surface, this line, it means. So it is equal to the dot product, that is the B dl cos theta. It is the dot, no? So it is the P dl cos theta. And here you can see, if you take this small length, okay, so see what is the direction of the B here in with respect to this current, because you know very well, using the different rules to find the direction of the magnetic field, it is always perpendicular to the current. Okay, it is perpendicular, and this line is again perpendicular to this line. So you can see dl and the B both are along the same line, that is the parallel to each other in the same direction. So that's why the angle between the B and dl is 0. So cos 0 is equal to 1. So we can write dot product of B and dl is equal to B dl cos 0, and cos 0 is equal to 1. So take out the B outside, integration of the dl, and from the Biot-Savart's law, B is equal to this value, and the integration of the dl, which is a small part of this circumference, so it is equal to the total is equal to the 2 pi r. R is the radius, so circumference is equal to 2 pi r. If we put integration of dl here, and the B is equal to mu naught I upon 2 pi r, we can see here the r is cancelled, 2 pi is also cancelled, so we have, it is mu naught I. So this is the proof of the Ampere circuital law. Now if the law is given, we have to apply practically also. So we'll discuss 3 applications of the Ampere circuital law. So first application, all these three equations or applications are in our syllabus of CBSE. So see the first application, how can we apply this Ampere circuital law in three cases. First is in case of the straight current carrying wire, thin wire we are taking here. If you see this diagram, again we have come to this conclusion that the DL and B both are in the same direction, so theta is equal to 0. So repeat the above line again, that is the integration of BDL is equal to BDL cos 0, cos 0 is equal to 1. So B and DL is equal to integration of DL is equal to, as we had done here above, it is the 2 pi r. Okay, so put here BD, integration of BDL is equal to B 2 pi r, and using the Ampere circuital law, line integral of the BDL says that it is equal to the mu naught I. It is mu naught I. So it is the mu naught I. So mu naught I is equal to B 2 pi r. Or from here we can write B is equal to mu naught upon 2 pi into I upon r, which is already derived in case of the Biot-Savart's law. This is the same formula. Okay, this is the first application. Now come to the second application, magnetic field of a long straight solenoid. You have already studied in class 10th about the solenoid. So solenoid, it behaves like a magnet and it produces a magnetic field around it and inside also. Inside the solenoid, magnetic field is always uniform and the magnetic lines are equidistant and parallel to each other. Clear? So now to apply the Ampere circuital law, we have to consider a rectangle closed loop. Okay, so A, B, C, D, and to find the magnetic field due to this long solenoid. So long solenoid means whose diameter is very less in comparison of the length of the solenoid. So that's why it is the long. Long term will be used when the diameter is very less. So now the total magnetic field can be found in this way. So line integral of BDL is equal to, we can resolve it, will determine the magnetic field due to the AB portion, B to C portion, C to D portion and D to A portion. Okay, if you see this line carefully, you can see here A to B, dot product of B and DL plus B to C, then C to D, and from D to A. A to B, B to C, C to D, and D to A. Okay, now here you can see this two, B to C and the A to D. These are perpendicular to the DL. So that's why the angle between the B and DL is 90 degree and cos 90 is equal to 0. So B to C, this one, B to C and D to A, this one, both will become 0 because cos 90 is equal to 0. BDL cos 90, both will be 0 here. Okay, and this C to D is much distance from the solenoid, so effect of the magnetic field will be negligible here. So we will neglect the magnetic field intensity due to the solenoid at this long distance. So we'll neglect because the magnetic field will be very weak in this portion C to D. So that's why the total magnetic field we have to consider, it is equal to the magnetic field produced by the A to B portion. Okay, A to B portion. So A to B portion BDL. Now we know BDL. So B and DL, we are considering this distance is equal to x. Okay, we are considering this distance as a x from here to here, A to B. So this is the distance x. And if we consider in every, see I naught, if I naught is the current passing through each wire, I naught, and x is the length, if there are n turns of the wire in the solenoid, so the total current passing through this in this solenoid, it is equal to nx I naught. I naught in current in each coil is turned, x is the distance in which it is flowing, and n is the number of turns. So the total current will be passing equal to the I is equal to nx I naught. So put here bx is equal to mu naught nx I naught. Why? Because bx is equal to mu naught I, and I is equal to nx I naught here. So if we cancel xx both sides, xx will be cancelled both sides. So it is equal to the B is equal to mu naught n I naught. This is the magnetic field due to the long state solenoid. Clear, students? Now one case you have to remember, useful in numericals especially, at the ends of the solenoid the magnetic field is always reduced to half of its value. So at the ends of the solenoid the magnetic field is given by half of this value, half mu naught and I naught. Okay, so remember this formula, useful in competitive examination as well as in numericals. Now the third application we can discuss, that is the magnetic field of a toroidal solenoid. Toroidal solenoid means it is the endless circular solenoid. Toroidal is a hollow circular ring on which a large number of turns of a wire are closely wound. Okay, so inside the toroid, magnetic field lines are always in the form of the concentric circles, like this. Okay, concentric circles. Okay, it is just like the circular loop. Okay, solenoid. So its magnetic field is always concentric circles inside the toroid. Now we'll find the magnetic field inside the core of the toroidal. That's why we'll find the formula to find the magnetic field. So again come here. So using the Circuital law, the line integral of the BdL is equal to mu naught I. It is the Circuital law says. So it is equal to the you can say, because it is the BdL cos 0, again the same direction. So you will write the line integration of BdL and DL integration of the DL as we had done in previous two applications. It is equal to 2 pi a, where a is the radius of this toroid. Okay, so now if we consider I is equal to n I naught. I naught is the current in each wire, current in each turn, and n is the number of turn. Capital N is the number of turn. So here we can write the B 2 pi a is equal to mu naught I. So mu naught I means n I naught, because we are taking I is equal to n I naught. Okay, mu naught n I naught. So from here we can write B is equal to mu naught upon 2 pi. Okay, n I naught upon a. Okay, this is the desired expression. Now to simplify, if we consider small n is the number of turns per unit length. What is the total length of the wire in the toroid? In the toroidal solenoid, it is equal to the n upon 2 pi a. 2 pi a, it is the circumference. So n upon 2 pi is the number of turns per unit length of the toroid. So put here n upon 2 pi a, n 2 pi a. So instead of this value, we can write here in place of this mu naught, and this is equal to small n, so mu naught n I naught. This is the magnetic field inside the core of the toroid. And dear students, remember always, very important for your examination also, the field of the toroid is 0 at all points except within the core. Outside every point the magnetic field is always cancelled, because the directions of the magnetic field produced by this portion will be cancelled by the magnetic field produced by this portion. So the magnetic field around or outside of the toroid will always cancelled. So magnetic field of the toroid is zero at all points except within the core. Within the core, the magnetic field is given by this value. Otherwise, magnetic field due to this toroid is always zero. Always zero. Remember this point. So dear student, this is about the Ampere circuital law, very important for your exam. And in next video we'll discuss the Lorentz force, etc. That is the magnetic force, very useful for the exercise questions also. Thank you, students.